Alright guys, let's see how we can solve another question from the fourth chapter of the Engineering Mechanics by Meriam. And in this one we have a specialty tool that is used for installing and removing snap rings. We need to determine the spreading force F applied at point G and H, knowing that our force P that is applying to the handles is 50 newtons. So as always, we're going to start with the free body diagram, and we can start with the free body diagram of this part of the lower handle in here. And if we draw that, so we're going to have something like this, where we have point E, which we have a pin. So we're going to consider two components, one along y-axis and one along x-axis. So we can call them EX and EY. We're going to pick just a random direction for now. We'll figure it out later. And also we have the pin D, which is kind of connected to member CD. And if we look at the member CD here, we'll see that it's a two-force member. And the main takeaway from the two force member is that the force will be along the line that connects the two ends of that member, which in here it's going to be something vertical. So let's just consider in this direction again for now. So we're going to call that D. And obviously we have our force P, which we know is 50 newtons applying on the handle. So looking at the free body diagram, we're dealing with equilibrium, so we can use our equilibrium equations, and by a simple look we'll see that we only have one x component, which if we do sum of all forces in x equals 0. Since we are in equilibrium, that shows that Ex is actually 0. So now we have two unknowns. Let's just do the moment about point D counterclockwise positive, and we should be able to find the EY in here. And if we look at that, we'll see that the moment of EY would be counterclockwise, so positive moment EY times the distance between D and E, which we know is 16 from the question. So we already have the vertical distance. I'm not gonna do the unit conversion for millimeter because it will be cancelled out at the end. And we also have the moment of the force P about D, which this time we have a clockwise moment, so negative P is 50, and we're gonna have the distance between B and D, which is 60 millimeters, and that's pretty much everything. And the reason I didn't do unit conversion is that because if we just divide this by 1,000 to get them in meters, it won't make any difference in our equation. So we can find EY in here, which is gonna be 50 times 60 divided by 60. So this will be basically 3000 divided by 16, which is going to be 187.5 newtons. So we did not get any negative sign. That shows that EY is actually upward. So that was a correct guess for EY, and obviously has to be D has to be downward in order to cancel out these two if we do our FY, but we really don't need to find D. What we care about now, we're going to move on to the second member in here in order to find the force at G and H. So it's basically the force that is applying from the ring to point G and H of these two. So now we care about the free body diagram of this part, and since we have E now, we should be able to find the force at G, and obviously whatever we get for G will be the same for H as well. So let's see what we had at E. So the force that was applying from the member EFG was in this direction, so that was correct. But like we're gonna have an opposite force to what we found in the previous step in here based on the Newton's law. So this would be our E, so this is gonna be downward EY. So that's that. We have the force that is applying at point G. We can show it something like this. And we're going to consider one force F in here. And you might ask again, since we have a pin at F, we should have two. And you're correct, we're going to consider two. But same as the previous step, since If we only have one x component in here, if we can do the sum of all forces in x, and I'm showing these in different colors, we can apply our equilibrium equations for each single member that we are considering in these machines. So from the free body diagram that I showed in red, fx will be 0, and we just need to do the moment about point F in here, because that way we're going to find the force at G, which is what we are interested. So the moment of G about F is counterclockwise, so positive G. We have to find the distance, or I should say vertical distance, from G to F. So this will be the line of action of the force, and we have that 33 millimeter. That's that, and we also have the moment of EY, which is also counterclockwise, so another positive. Our EY was 187.5 from the previous step. And the distance from E to F, again, the vertical distance to the line of action, which is what we have in here, 32 millimeter. And this will be equal to 0. And now we can find our G. We're going to get a negative sign, which shows that our assumption for the direction is not correct. Now let's see what we get. So times 32 divided by 33, that's gonna give us 181 plus 82 newtons. And obviously we have a negative sign, which shows that the correct direction for G is actually downward. And same thing for the H. So we're gonna have something like this in here and something at H in this direction. So yeah, that's pretty much everything for this question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.